Okay, so today we get the quiz, but that's the last one for the DC. From now on, we deal with the AC only. The thing is, we right now online. So that's why I recommend, even you already get through the stuff here, but I still recommend you better uh, try to do it over. That will be happy. However, if you think you already know it, then you don't have to be in the Zoom. Okay. Next semester, that means from September, that can that not happen anymore. That means we return to the class and you will be doing on the lab. Right now, we cannot doing the hardware lab. So that's why, like you when they take the student to learning about that equipment, you already know. You don't have to be there. Okay. The thing that we try to take for the new student. Okay, so if I go into the handout, uh, and if you get a question, go ahead and stop and let me know. So I will be trying to get through it. Okay. So the first thing today we're learning about capacitor. And it's a capacitor circuit component designed to store electrical charge. If you connect a DC voltage source to the capacitor, then the capacitor will charge to the voltage of the source. The capacitors are widely used in electrical and electronic applications. They use in electronic systems for signal conditioning and the timing. Okay, capacitor could be either non-polarity or the polarity. So this is the show to some uh, picture on the capacitor. So when you're working, you see that you can recognize that the capacitor. Okay, there's a different type. And normally the value of the capacitor is the farad. Okay, and also you can get the millifarad 10 minus 3, microfarad minus 6, nano 10 minus 9, and the pico minus 12. Okay. Now, try to see. Uh, you can see this is the circuitry here. Okay. You get a switch in here. They can connect to position 1 or position 2. Okay. The first one, when they connect into position 1. Okay. So they're telling you, you get a voltage E here. Okay. They send the current through the resistor R and they will be charged to the capacitor. Okay. And capacitor will be a positive here and negative here. Okay. So for the long time, what the voltage on the capacitor supposed to be? Who telling me? Take long time. So what the voltage on the capacitor VC supposed to be how many volt?
Is another source.
E.
They will be equal to the power supply voltage here. Maximum cannot be higher. So if you're looking into here, they're showing you, okay, when we close the switch, before they still voltage on the capacitor, that's for VC, and the voltage on the capacitor will be keep charging up, okay, but they cannot go quickly. Take a time, keep going up, okay, up to the certain point, no more charging. Voltage already same thing with the E power supply voltage, okay, so they call it transient interval or steady state. Steady state, that means no longer, okay, charging. So time constant. Time constant, that means tau equal R times C. So every time you're working with the capacitor, then you have to know what that means for the time constant. Okay? So time constant is the time for the capacitor charge or discharge to 63.2% of the maximum value. Okay? That is the definition for time constant. And in the formula calculation for the time constant will be equal R and C. In this formula, R must be in ohm and C must be in farad. Okay, if you get a different unit, you have to convert it. And they say after the 5 time constant, the capacitor will be full charge. Okay, any question about the capacitor charging, DC charging? No question? So maybe easy, right? And now you see the capacitor will be discharging. That means when they move the switch go to position number 2. Okay, so no more power supply. And the voltage charging on the capacitor now they will be discharged. Okay, they will discharge through the resistor. Okay, so you can see when they slow it, the maximum voltage the same with the power supply voltage E, and now they will be discharged. They not discharge quickly. Take your time. Keep going down, low and low and low and low and low. This is exactly in your car battery. If you turn on the headlight and do not forget to turn it off, next day your battery will be empty. Okay? So that's why they keep discharge until they get zero. So this will be telling you this part will be charging and this part will be discharging. That's a very simple thing. Okay? The capacitor they can be charged or they can be discharged. Okay? Now, this is I given you the formula, a little more detail, but we not apply at this time. When you learn go to the textbook, then we will be given to you detail to working on this thing. Okay? They say the rate of capacitor charge it depends on the product time constant. Time constant is the time for the capacitor charge up 63.2%. of the maximum value. And after 5 times constant, again, capacitor have to be full charge. Okay, so on this calculation here, apply for the formula here. Okay, for that one, the definition here, but I just bring it up here for whoever you want to read. Okay, on this example here, they given to you equal 40 volt at 200 ohm. Okay, and C equal 1,000 microfarad. What you need to do for me? Calculate the time constant first. Calculate the capacitor voltage at time constant second. Okay, only number 1 and number 2. We don't want to do number 3 and number 4. That will be using the formula I just give it to you. So make sure you know how to calculate the time constant. Calculate it, tell me what you get. Make sure everyone want to learn how to be in the Zoom for the lecture on the AC if you're not already done. Otherwise, you will get lost. I think I will not coming back on this thing at this semester. Okay, who get the time constant?
200 milliseconds.
How many?
1 second.
The answer will be 1 second. Is it right? And they get a difficulty for calculation. Then just bring it up.
Mr. Pham, time constant is R times C, right?
R times C.
So there was 200 ohm times 100 microfarad. So it definitely cannot be 1 second.
No, it's 1,000 microseconds.
Two.
You say 1,000 microseconds minus 6 and minus 6.
1,000 microseconds times 200 is 200 milliseconds.
Right, so it's not going to be 1 second.
Right, it's not.
Okay, so that will be the answer I given here. It's wrong. Okay, make sure, okay, you get the time R times C.
200 ohms times 1,000 microfarads is 200 milliseconds.
1,000 times 10 minus 6. Okay, what equal?
200 milliseconds.
You get 200 milliseconds.
Correct. Hey, Mike, did you get the
Agree.
same thing?
Yes, agree.
Okay, that means we try to make sure we get the right answer for, not get the answers yet. Okay, and the capacitor at the capacitor voltage at the time constant. What we see. at the time constant. So VC will be equal 63.2% at maximum voltage. So what you get? The 25 or what? I don't know. I have to calculate it. Let's see, 40.
25.28, Mr. Pham.
Okay.
25.28.
25.
0.28.
All right.
0.28.
Okay. So do you have any question on number 1 and number 2? Go take that one. We don't care that.
Why do you have to divide by 100?
The thing is, they say 63.2%. You understand? They say 63.2%.
Okay, got it. It just wasn't written out.
Yeah, you have to divide by 100. Yeah, anyone get a confusing, just bring it up to make it clear. So when next time they ask you how to do the calculation, then you know how to do it. That's a very, very basic minimum. Okay? We don't want to go too many details. We don't need them. Okay? Now, for the capacitor connect in series, if you connect in a series, C1 plus C2 plus C3, okay, the formula, they will be opposite to the resistor. So C total will be equal 1 divided to 1 over C1 plus 1 over C2 plus 1 over C3 and so on. Okay, they lay the resistor in parallel. Okay, if they get only 2 capacitors in a series, you can use this formula. C1 times C2 divide C1 plus C2. Okay, and now if the capacitor connect in parallel, formula to calculate will be the same resistor. Capacitor total equals C1 plus C2 plus C3 and so on. Okay, that's just a formula. Now, you can do this for me. Okay, for this right here. For the circuit below, they want to calculate the total capacity. Go ahead and calculate and see you can get the answer we wanted.
Well,
What you get?
I got 12. I don't know.
All right.
Yeah. The answer is at the top. 12 microfarad.
Right. But I'm asking for the calculation. You know how to calculation to get that value.
Yeah, I know.
Okay. That's what I want.
Okay.
We already given you the answer, but it not means you get that answer only. I want you to say how do we get into that?
You add C4 and C5, and that'll give you one. And you add C2 and C3, and that'll give you another one. And then you use that formula for like you would do for parallel resistors, and that'll give you the final answer.
Yeah, that's what he said right here. It's a parallel, right?
Right. So you add those.
Them up. Okay. When you add them up,
You get 60.
series, right?
Right.
The series, then you calculate the series for only two capacitors using C1
Well,
times C2.
well, C4 and C5 is in parallel, so you add those up as well.
Okay, now 45 and 15 micro parallel. How can you get
60.
total? Then you add them up, right?
Right.
Yes, 60.
60.
Right, you add them up here. So forget it, guys.
It's capacitor, not resistance.
Okay, so they will be 60, right?
Right.
Yeah.
Right.
So now 60 and 60.
Half of that is 30.
In
30.
30,
30.
you combine this guy. What you get?
30.
30, 30.
30.
60 series with 60.
30.
You get 30 up.
Right.
Okay, so they will be 30 micro farad. Okay,
Mhm.
how about this, you guys?
That's 20.
20.
So they will be 20. So now you come up with a one right here. You get, sorry, you get 30, right?
Right. Well, you get 20 for 8 and 12 is 20.
Okay, then you get another one here. Oh man. A 20, right? So
من هيك نزلوا سعره 1.56
it
نستنا
30 times
20
8.
over 20, 30 plus.
So what you get?
12 microfarads.
Okay, the answer will be here.
How do you get 30 for the first one if it's 60 and 60?
Because when you have two things in parallel, and if they're the same value, you just cut them in half. If you had one was 40 and one was 40, you cut that in half as 20. If it's 60 and 60, you cut that in half as 30. If it was 80 and 80, you cut that in half as 40.
Okay,
They the same values.
you get that guy here and that guy here. 160, right? Another 60. So you calculate like the formula that will be C1, C2, for example. Then C total for this one using C1 C1 times C2 C1 C2. So that's why you get 60 times 60 divide 60 plus 60, and that given you 30. However, Normally, whenever you get two capacitor in series with the same value, and the total will be a half of that. You don't have to do calculation. Like you get a resistor the same if they parallel. Okay, get the same 50 ohm, 50 ohm. Then you know for sure equivalent will be 25. That's the same apply for series capacitor.
Mr. Pham. So is that supposed to be a capacitor in the middle of those two that are in parallel?
Can you say again?
Yeah, is that supposed to be a capacitor where the two capacitors, one's 45 and the other is 15? Is that supposed to be?
Parallel. That parallel.
No, I'm talking about the symbol. When you combine them, it's supposed to be another capacitor, right?
That one 45, 15, right?
Yes.
Yeah, parallel. So you have to adding up for capacitor.
Yeah, I understand that, but the symbol, you had a resistor there. Was that supposed to be a capacitor?
Yeah, that's what it should have been.
Okay, I got it. Thanks.
Okay,
What-
question regarding to this problem.
Yeah, I just have one. Because the 60 microfarads that's in series with the parallel ones, and it just is all straight connected, you can treat it like it's just like one unit, and then do the same kind of divider thing with the next series in parallel.
Yeah, that's a way too easy to do.
Okay.
Don't try to combine everything. And that gives you the formula more complicated. We don't want to using the formula 1 over, 1 over C1, 1 over C2, so far. This is a more easy way, simple way.
Okay, thank you.
You are welcome. Okay, now capacitor again. Capacitor current and the voltage during charging. Okay, so if you're looking on that thing here, this will be during charging here. Okay, okay, after charging, and they will be discharging. So basically, when I'm looking into this one here, so basically current decay at the capacitor charging. So they're talking about the current, okay? And on the other thing, we already calculate during the voltage, okay? Now this one here. For the voltage, capacitor voltage, VC equal E when fully charged, okay? This data for a reference. So for you guys to understand a little more here, you get a sideway here. Okay, that's a complete one cycle. So if you're talking about a degree, so this will be a 0 degree. At this point right here, you're going down 90 degrees. Right here, 180, 270, okay, and 360 degrees. So they given you also for the radian, 90 degree equivalent to pi over 2. Pi will be equivalent to 180 degrees, okay? And if you get up to a 360 degrees, they will be 2 pi. Basically, how can you AC signal? How can you get a sine wave? That coming out from what?
The oscillator scope.
How come you get a sine wave where the signal coming out? Basically, they coming out what they call a AC generator. Okay, AC generator, they get the rotate inside the step, rotate inside the AC generator, and they converting into the electrical wave. So when you add the right, it is 0.0 right here. So basically, in electrical, you get a 0 here. When they moving up, go to them at this point 90 degrees. So that's why they keep going up to 90. Okay. When they go into the other side, 180 degrees.
Mhm.
Okay. So that's why you get 180 degrees. And completely here, you go back into 360 degrees. Okay, 360 degree or 0 degree will be the same. Okay,
Hey, Mr. Pham, is that all? That's also how you generate the positive and negative half cycles, isn't that correct?
the half cycle for the pi, right?
Yeah, on your signal from 0 to pi.
Hmm,
Is,
that's a half cycle.
yeah, right. And that's the positive half cycle.
Yeah, it's that you're using 180 degrees,
Right.
using pi
Mhm.
or 2 pi. 2 pi equivalent to 360 degrees. Okay, that normally for most of the students when you go to the college, then you have to deal with that. I think that they will be go more detail. Okay, they just a reference. Real relationship between omega t and the frequency f. Omega t equal 2 pi radian. Then omega will be equal to pi divided t, radian per second. Or omega equal 2 pi f. Okay. Note that omega is reference to f radian per frequency. We're not using much in this program. The thing is, they have to using later on in the college when you have to learn trigonometry. Okay.
Mr. Pham, what does the W stand for?
Which one?
The W, what does it stand for?
Omega,
Okay.
radian frequency. Now we're talking about capacity circuitry. That is what you need. When AC sinusoidal applied to a capacitor circuitry, the capacitor creates a resistance we call a capacity reactance. IC. Okay, for the resistor, they get the R for resistor. And a capacitor also, they will be get a resistor. When you connect AC circuitry to that, but they get a resistance they call a capacity reactance. IC. Represent the opposition that capacitance present to the current for sinusoidal and calculate in the formula. Okay, so if you want to calculate the resistance of the capacitor, IC, they call a capacity reactance. And the formula will be equal to 1 over 2 pi FC. Okay, in this formula, pi equals 3.142. And F must be in hertz and C must be in farad. Okay, the relation between capacitor voltage VC and the capacity current IC for pure capacity circuit, current will be least voltage by 90 degrees. Okay, now let's see. This is a formula, okay? They coming from experience. Don't ask me how. Okay, now when you see the display on the coordinates here, so this the red one, that's the voltage of the VC, capacitor voltage. And now the blue here, that will be displayed for the IC current. Okay, and IC current, you see, they look like this one. So they coming to 90 degrees, okay, before this guy, pi over 2 mean 90. So that's why they say current IC on the time will be leading voltage VC by 90 degrees. That's a 90. Okay, that's what you have to be memorized that. So when you're doing a PSPI simulation, you can see they will be exactly. Okay, that means IC on the time will be leading VC by 90 degrees. Now, they're talking here by capacity reactor. IC equal 1 over 2 pi FC. Okay, example 1. For the circuit shown, okay, for this circuit here, they want you to calculate the IC. Go ahead and do that calculation for me to see who get it.
Twenty-one, 22.
You get 21, 22?
Yes.
Okay, one student get the 21, 22, what unit?
Well, that's, you can make it 2.12K
What unit?
or something like that. And then it's ohms because it's X sub C.
Okay, you said 22, 21?
No, 21, 22.
Okay, one student get 21.22. What? Is it right? Is it what you get, right?
No, 21, 20.
I got 2122 ohms, which is equal to 2.1 kilo ohm.
Yeah, no dot there.
21, 22 ohm. Okay, if they want kilo ohm, divide by 10.
In other words,
Divide
that
by
would be the same.
1,000, not 10.
Yeah, that would be the same as 2.121 or 122 K ohms if you put it in that form.
And now, number two, they want to know the current I. So now the thing is that at this time here, you get IC, okay, equal 2.12 K, right?
Right.
2.121 KO. So now they asking you, what is the current? Who know how to calculate the current?
Oh, the current, it's Ohm's law, so the current would be VT divided by X of C.
Perfect. The thing is when they get the IC, that means they just like the ohm, okay? Then you can using the Ohm law. So current I basically equal, okay, V total.
100 divided by
So
2.121.
I see, okay? That means 100 volt divide 2.121. Okay, or you can say 1, 2, 1, 2, 1. So how many milliamp? Or how many amp?
47.
Okay, so basically 100 divide 1 to 1. So that look like 0.047, right?
47 milliamps.
Okay, look like 47 milliamp.
Right.
The thing is we try to do calculation. So later on, when you try to review, you know how to do your calculation. This is a very, very basic. You have to know how to do it. Okay, example number 2. For the circuit number 2, okay, they want to know the capacity reactant IC. When they given to you the frequency equal 3.183 kilohertz and the current I equal 20 milliamp. Okay, who get the IC? How to calculate IC?
VT over I.
Perfect. Mr. Smith, really smart today. So you understand a V, let's say VT, right?
Right. Divided by I.
That equal IC. Ohm law, same thing. When they get a like the resistance value ohm,
Mhm.
then just using Ohm law. So what IC you think you get?
You get 10 volts divided by 20 milliamps.
Okay, so 10 divided to 20, 0.5. 0.5, that means you divide it, they be milliamp. So 0.5 times 1,000.
500. Oh,
500 ohm. Perfect.
That's what I got.
And now they want to calculate the C. Number 2, calculate the C value. How do we calculate the C?
You gotta flip flop the formula around where you got X sub C equal 1/2 pi
Yeah.
FC.
I
So
hear.
C would equal 1/2
Okay.
pi 1/2 pi frequency X sub C.
Okay, so C over 1 over, right?
Right.
Over 2 pi
Pi
C.
FXT.
Yeah. 2
Pi frequency XC.
I see. Okay, so who can get the answer? Let me know.
Three, 1, 8, 3, 0.1 microfarad. Did anybody get that?
I got that too.
0.1 microfarad.
Yeah, it is.
Okay, so someone get 21 microfarad.
0.1, not,
no,
it's 0.1
0.1.
microfarads.
No.
Tell me
0.1.
0.1, right?
0.1 microfarad.
Okay. Farad mean microfarad. The thing is, most of the time you have to redo it again, 1 time or twice or more, in order to understand. Okay? Go.
Yep.
Now, this one just a formula given to you a little more here. Now, if you get a capacitor C1, C2 in series, however, the value will be IC1, IC2, IC3. So when you want to combine, just add them up. The thing is IC1, IC2, IC3 will be in O. Okay, so you can see the formula we're using before. Okay, when the capacitor in series, you're using 1 over C1 plus over C2. However, that's the value of the capacitor. Now, if they already be calculate IC1, IC2, IC3, so they work perfectly, exactly like the resistor in series. Just add them up. And the same thing, if capacitor in parallel, they get the value for the IC, then they working exactly resistor in parallel. Okay, so if you want to doing calculation, you can looking into this formula. Now we go into the point here. First thing you will be learning capacitor, resistor circuitry in series. Okay, try to see how many things will be. You will be learn I and C in series, and then I and C in parallel. Okay, then you will be learn inductor L and C in L and R in series. L and R in parallel. Okay, that is a second thing. Next thing, we'll be learning RCL. That means combine resistor, inductor, capacitor in series. Okay, and RCL in parallel. Then that means cover for the LC, RLC circuitry. Fourth thing today, we'll be learning about RC in series. So now you're looking into this circuitry here. The capacitor, they get actually 80 ohm. R will be 60 ohm. Okay. Now, the current IT is the same in the components. The thing is current go to C or go to R will be only one current. Right? That will be telling you what? I total equal I C equal I R. Right?
Mhm.
If the current go through the capacitor, that will be IC. Or the current go to resistor, you call IR. But this is series circuitry. You get only one current. Okay. Now, the voltage across the capacitor here, we say that will be VC. Okay. And the voltage across the resistor here, you say VR. So as I already know, IC will be least VC by 90 degrees. Is it right? IC least VC 90 degrees. That will be telling you IT will be also least VC 90 degrees. Correct? The thing IT, IC, the same thing. That will be telling you another thing. IR also lead, okay, VC 90 degrees. Is it correct?
Yes.
Okay. Okay, now, what relation between IR and VR?
They are in phase.
All right. Resistor, they get a no phase difference. Okay. For circuitry with the IR and the VR, they will be in phase. Now, I can draw that for you. How cool. Okay. If you get this AVR, and then you can get the ATIR. You see that? Both going up or both going down. That's what they call in phase. Okay?
But the magnitude of the I is bigger than R, right?
It doesn't matter, depending on the circuitry.
Mhm,
Right now, I'm talking about the phase, the angle.
mhm.
That means resistor, voltage, and the current on the time, they will be in phase. Okay? And now, if you're looking here for the VC, okay? This is the VC here. VC. And this is 180 degrees, 90 degrees right here. So I see they will be go this one. Okay. So that will be IC. IC going to 80, 90 degrees. Okay. Before the VC. So that's why IC lead VC 90 degrees. Okay. And now then you can see on this circuitry here, you get one go this way, the other one go this way. That will be V, that will be I. What that mean here?
180 degrees out of phase?
Out of
Phase.
phase. I try giving you the definition. Okay. When you look into the circuitry, you understand they will be in phase or they will be out of phase, or they will be which one is leading to the other signal. Okay. So VIR will be lead VC90. Okay. And
VC lag the current.
they say VC equal IT times XC. VR equal IT times R. So, okay, in here they say VC IT times XC VR equal IT times R. Okay. So, what they try to figure out what the relation between R and XC.
90
They
degree.
will be in phase, or they will be out of phase, or they will be a different phase. How come? Who can tell me? I want to know the relation between R and XC. Is it in phase, or if it's not, then what happened?
90 degree out of phase.
They out of phase right here, right? They say 90 degree out of phase. I agree. However, which one will be leading?
VR.
Now I asking about I and C. I see.
C will be leading.
R and XC cannot be the same phase, we know. However, which one will be leading?
The C.
R
R will be leading.
R will be leading, correct?
will be ready. Yeah.
I telling you how. Now, what happened? R and IT. What the phase? R and IT.
In phase.
In phase.
Same phase.
Perfect. In phase. How about IT? Okay. And the IT time XC. Okay. Are in phase with the IT. IT will be same IC. Okay. IC leading. Okay. So VC by 90 degrees. So that will be coming up with the R will be leading VC. Okay. I put it here. Lead VC 90 degrees. Now we see this one. Okay, a little harder. This is basically rectangular for a coordinate. So this normally they call a real X and Y. And I call that just a real. So you understand is going up here how many degrees? This one. How many degrees here?
Beating what?
90. 90?
Right? This is 90 degrees. Go up to here. How many degrees?
This one? One?
180.
180.
Hmm.
Going another round up here. How many?
270.
270. Go back here.
What here?
360.
Yeah.
Then completely one circle here. Okay, now. So if I say, you can see I can draw this one here. So I say this angle here. Theta. Okay. So that they will move around. Go here, 90, right? Go up to that point, 180. Go up to that point, 270. Go back to here, 360 degrees or 0, same thing. Okay. And now, if I draw R here, that's for R. Then now how come I draw for XC? If they going up here, that means they leading 90 degrees. Okay. However, we already said R will be least XC by 90. So XC must be going down. With the angle here will be minus 90 degrees. Okay. So now what we need to draw vector R here. I start from here. R go this way. Okay. XC going down here. So when you get to draw that, you get XC, and the phase angle here will be a theta. Okay. Now, in this rectangular, in this triangle here, if you want to calculate the GT, how do you calculate it?
Pythagoras.
Pythagoras. if you're learning the math. Okay, then they go up using Pythagoras. Square root of what?
R squared
R
plus X squared.
squared.
That is how to calculate the
ZT, impedance.
T in this case. Okay, so now if I, who know in something telling me, if you want to calculate the sine of theta, sine of that angle equal what? Cosine of that angle equal what? That's a definition. And tan, that in a try,
Yeah. X sine is XC over XT.
that's what you need to know. That's a definition. Sine theta equal, that is sine of the angle theta here, equal XC, right? Over what?
R,
ZT.
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 How about cosine?
R
Where ZT?
Exactly. If you know something about the math, trigonometry,
Yeah.
okay,
Not
that will be R divide G total. How about tan theta?
XC over R.
XC over R, yeah, that's a tangent.
Of R. That if you don't know, this is a formula you must know. We don't care how come you get that. Okay. So
Your ZT was equal 100.
what you say? GT.
ZT is equal 100.
I'm not come up to that point yet.
Okay.
Okay, now you can see, I can tell you, in this circuitry here, this is 80 ohm, and this is 60 ohm, and they want to calculate the total resistance, total impedance. Okay, now you get along with what they call an impedance.
黑这个声音就是黑的
When
黑这个声
impedance for R, okay, for R you say resistance, right?
Right.
Resistance. For the capacitor, I see reactant, capacity reactant. Okay, so when you're using impedance, even they still old,
100 ohm.
yeah, I know. But the thing is, what my question is, when you want to talking about impedance, I say
Generally, when
DT,
we deal with DC,
that means the impedance. How? How come you
When
not say resistance? How come you not say reactant? You say impedance.
it's a combination of reactance and resistance when you are dealing with AC.
That means
Right.
whenever they combine, okay, I see, then they will be get the name impedance, okay, or will be HL for inductance, then they will be called impedance, okay. So how come you cannot like 80 ohm adding to 60 ohm to get a total? How come you cannot do it?
because because
Because
The
they're out
R-
of phase.
yeah, the R doesn't have a phase, and the
Yep.
X of C and the X of L does.
The reason you cannot add them up, the thing is they not the same phase, right?
Right.
One will be leading another one by 90 degrees. Okay, so in order to doing a total impedance, that's why you have to using the formula I just given to you here. R square plus H square. Okay, so the answer equal to say 100, right?
Right.
So the answer will be 100
That's for ZT, for ZT.
or GT, sorry.
ZT. The current would be 1 because it's 100 volts over 100 impedance. So
That will be equal to 100 ohm.
100.
And this is easy, right?
Right.
GT will be 100 volt. Divide 100 ohm
Equal 1
equal 1
amp.
100 volt is RMS, yeah?
Yeah, that's on AC. Okay,
Yeah.
that means supposed to be VIMS.
Hey, Mr. Pham, in the past, you said VAC and VRMS is the same thing.
Exactly.
So since that's VAC, that's, well, it's RMS.
Yeah, normally you study electronics, then you know VIMS. But really outside, they using VAC.
Right. Same thing.
Okay, identical.
What's RMC, Joseph?
No, he said RMS, root mean square.
Thank you.
We already talking about that, right? VIMS or VAC, identical.
RMS is 0.707 times the peak.
Okay, now, if you want to calculate the VR, okay, VR equal IT time R. Okay, if we calculate the VC, then you can using IT time XC. Exactly, I gave it to you here. That's easy. Okay, now, last thing on this one. They want to doing calculated for angle theta here. Okay, the angle. They want to calculate that angle to see how many degrees. So what is that angle for?
Phase difference between a resistance and capacitor.
There will be a different phase between what?
Voltage and
current.
current.
Make it more clear.
Voltage and ampere.
What?
Voltage and current.
How is the current is leading or lagging the voltage and current?
You have to tell, you say voltage and the current, right? That's like identify for me. In here, you get a couple of different voltage. V total, VC, VR. You get one current, I agree. When you say the angle to the here, the difference between the voltage and the current, I agree. But what voltage, what current?
VCIT.
No. You already know VCIC.
IT.
IT. IT, I see the same here.
Yeah.
right?
Yes.
So IC will be leading VC 90 degrees.
Yeah.
That's telling you IC and IT will be leading VC 90 degrees.
Basically, it's the phase difference between the voltage of the resistor and the voltage of the capacitor.
No,
No?
no.
Hey, Mr. Pham, just a quick question. Down the bottom, you said IT lead VT by by theta degrees.
I
On your handout.
Yeah, IT leading VC 90 degrees. That formula.
Is it something regarding a resistance and capacitance
No,
angle?
no.
You're gonna have to tell us, Mr. Pham.
Huh.
Can you repeat your question one more time so the question becomes more and more
Yes,
clear?
please.
Okay, now on this circuitry, I know for sure. You know the volt VC and IC. IC leading VC 90 degrees. Correct?
Yeah.
I and V are in phase. See that? They're in phase.
Yes.
No different.
Yeah.
We come up with R and IC. R will be leading IC 90 degrees. And
Yep.
we still have to do calculation the angle here. So that angle stands for angle difference between what?
ET and BT.
R and XC.
The difference between VT and IT.
IT. Yeah.
VT and IT, they not in phase, but they cannot be which one is leading 90 degrees,
Depend on the
but they differ. So that's why the phase angle here, that means the angle between total voltage and the total current. Okay?
And since we're dealing with a capacitor, the total current is leading, correct?
Yeah, total current, IT and IC will be the same. Only one current.
Correct. So then IT leads the voltage.
That means IT will be leading VT, but not
Correct.
90 degrees.
Oh,
Will be
okay.
leading by the phase angle here.
Okay.
depend on the value. Yeah.
Okay, now calculate telling me what you get angle. That means you can get tan theta equal minus XC. XC equal what?
80.
1/2 pi FC.
Divide
Well,
R will be 60.
60.
Okay, then now you want to calculate the theta here. Okay, they will be take the 10 minus 1. Okay, of minus 80 over 60. Tell me what angle equal.
Minus 53.13.
Minus 53.
3.13
3.
degrees.
That's just like the formula. Okay, you get along with that course will be very, very simple. Not like electronic, not like a digital. Just a very basically for the AC circuitry. Okay, finally, the phase equal minus 53.13 degrees. That means the phase difference between the total current and the total voltage. And in this case, the total current will be least voltage, total voltage by 53.13 degrees. Now, your job, do it for me. Oh man. I will be stop here. We'll be continuing next Monday. Okay? But you try to do the example, this example. And also you can try to do assignment AC review 1, AC review 2 related into this problem here. Okay? So now I need to stop my lecture so you guys can take the quiz. Okay, so Mr. Sam,
Yes, Mr. Pham.
I will be stopped there, right?
Yes, sir.
Okay. Now you can go ahead and do it.
Okay, thank you.
Okay, thank you.
Let me go ahead and do that. Okay, we're going to be running. Let me go ahead and share my screen. It will be this one here. Okay. So we're going to be running the test. So we're going to be, okay, so slideshow, start from right now. Okay, can you all see the test?
Nope.
No? Okay.
Yes.
Let me,
Yes.
yes?
Yes, it's there.
Okay, very good. All right, go ahead.
How come?
Right now I see it.
Say no.
Now I see it now.
Make sure Monday no test, okay? Just review this test. Only one test per week.
Thank you.
Give your guy a little flexible time. Get more time to do something else. Now you just enter the value. No multiple choice.
Do or die.
Don't look on my paper.
I won't. Later.
Yeah.
Sam,
Yes.
Mr. Yi?
Hold on. Hold on. Victor first.
oh, Sam, the 4.1 that the unit says amperes, it should be ohm.
On 4.1, they want the R total, right?
Right, but on the actual test when we downloaded,
Yeah, yeah. Just ignore that. Just yeah. Just think about that. Just ohm. Okay, I will make that correct. I will.
okay, just want to let you know. Okay.
Okay, thank you. Okay, Jen, you have a question?
Can I see the first one again?
I have to wait until this one comes to an end first before I can go back to the first one. Okay.
Okay.
Okay. All right. So let me go ahead and go to number one.
Thank you.
You're welcome. Okay, so that's number one.
Excellent.
It was a total of 4 of those blocks, right, Sam?
Excuse me?
There was a total of 4 blocks, correct?
On which one? The last one?
Block 1, block 2, block 3, and block 4, correct?
Yes. So if you look at the number of slides, yes.
Yeah, okay, got it. Thank you.
Okay, you're welcome. Okay, so anybody have any other question?
There's a bunch of A
Read the
papers.
chat. Look like everybody's good.
Hey, Sam,
Yes.
when is this video gonna be uploaded? I feel like it's gonna take me a minute to do some of these.
Yeah, it's Mr. Pham will upload it as soon as we we finish with this, and he goes a little bit editing, and then he should be posting. Yeah, it should be posted by tonight.
Okay, great. Thanks.
Okay.
Okay,
Thank you.
bye.
Okay, thank you. All right.
Okay, the thing is, what I'm saying is, I don't want to fail anyone. Only thing is you work.
Yeah, just try it. You know, try your best at it, and try to just give a run at it and see what how you can do, and then
that's why
after that you learn a little bit.
I
as you
will
go.
be uploaded video so you can redo it. Okay?
Yes.
Okay.
Okay, good night.
Okay.
Bye for everybody.
Thank you. Have a good night.
Hey, Mr. Risa. Sam,
Thank you and good night.
good night.
Good night.
Do you know anything about Risa?
Richard, yeah, he just he's gonna be just sitting in the background. He's not going to do participating as much anymore, and just
okay,
because like I said, it's a lot of review, and he's yeah, it's a lot of review for him. And
Hello.
yes, Oscar. Do you have any question?
No, yeah, I just wanted to mention that I was with you guys.
Yes.
But the thing is, the Cadillac converter in my car got stolen.
Oh, wow.
And yeah, that was something else. So I really got distracted, and I just, I know I didn't talk much during the session.
Yes.
I do have a lot of questions. I'd rather email them to you. I don't know if it's more convenient. But
yeah, you can email to us, or you can call us, or you text message us, and we can always work with you. Okay.
Okay. All right. Cool. Well, yeah. Watch your Cadillac converters. They're taking them. Yeah.
Yeah, it's popular right now. It's in very high demand. And
what type of car was it?
I think any car that they look at, any catalytic converter, the price on it per ounce wise is pretty expensive. So
if they take mine, they're gonna need to make repairs.
So, good night, everyone.
Okay, good night.
Good night.
Good night.